Swayam Prabha. Digital India. Educated India.
Okay, good morning everyone. If you see me, it looks like, either it's raining outside or I've ran, right? So actually I had a quiz to conduct, exam, and then I had to go up different floors running. So therefore, that's the reason for my sweaty shirt. But okay, so yeah, I'm actually at the Department of Chemical Engineering. I had one slide. Okay, that's so that I had actually put in a brief stuff about myself, but then I think it was read out. So in case if you want to reach me out, that's my coordinates. I sit in HSB. It stands for Humanities and Sciences block, room number 151, and that's my email ID, basa@iitm.ac.in, and that's my phone number in case if you guys want to reach out at some point, right? So this is how I've structured, my talk. I'm just briefly going to tell a little bit about something called as a soft matter. I don't know how many of you have heard this term, soft matter. Okay, 1, 2, 3. Yeah, any idea what that is? No idea. Okay, so they've heard the term soft matter, but they don't know what it is. So I'm just going to start by defining what is soft matter, because it turns out that everything that around us, okay, everything that you can see things around us, including things in the industry, things that we use in everyday life, everything is soft matter. Okay, I'm just going to convince you that in the next 10 minutes or so. So if you look at the definition of soft matter, okay, this is given by a Nobel laureate, right? In his Nobel lecture, he basically defined soft matter as material that are based on polymers, surfactants, liquid crystals, and what are called as colloidal grains. Okay, I don't know how many of you know, whenever somebody gets a Nobel Prize, they give a talk for a general audience. Okay, and these general talks are very, very good, and there's a nice script for each of those talks, and they explain everything that the scientists have done in very simple words. Okay, and therefore I've just picked up this definition from one such Nobel lecture. Okay, you can go and take a look at that. So it turns out that these materials, right, the surfactants, polymers, colloids, and liquid crystals, they're actually added to different formulations that we use in everyday life for different purposes. For example, when people put colloidal particles, right, they're used. They're basically, if you look at paint, right, paint actually has a lot of particulate matter, which gives color. For example, if you want a white color, people put in TiO2, titanium dioxide pigment. If you want a red color, they put in iron oxide based particles and stuff like that. Okay, so basically they're added to formulations to kind of play with their flow properties and structure them in a different way. As all of you know, surfactants are actually added to a lot of cleaning products, right, because they help in detergency and cleaning stuff. Polymers are again added to tailor the flow properties. What do I mean by that? Whenever you take a shampoo out of your bottle, right, it comes out nicely. It doesn't come like water, right? If it comes like water, it doesn't have a good feel. What they do is they put in some polymers which regulate their viscosity. They make them little viscous. It looks nice. It comes out nicely and stuff like that, right? So, and therefore it is very hard to imagine a field which doesn't have any of these ingredients. Okay, you look at food, cosmetic, pharmaceutical, paint industry, fuels, so on and so forth. Okay, so therefore there's a lot of interest in studying these materials. IIT Madras itself has about more than about 30 faculty working in different aspects of soft matter. Okay, okay, so now, so the word soft matter, people also use a word called complex fluids. Okay, they are kind of used synonymously, and in complex fluids we are basically looking at length scales that's of interest is large than atomic scale, right? Atoms and molecules are, as all of you know, they are sub nanometer, right? We are looking at collection of, if you look at each of these things, they are made up of collection of, these nanometric scale materials, okay, and they are put together to form all these particles, surfactants, and okay, that's the whole field. And another way of defining what is a soft matter is something that is easily deformable. Okay, if you look at solids, right, okay, difficult to deform, right, and something like, for example, emulsions, or or ointment, for example, you can just take it in your hand, and if you just rub it, they easily deform, right? And the reason why they deform easily is because they respond to energy of the order of few thermal energy. Okay, I'm sure all of you may have heard this term, thermal energy. Any molecule, right, at a particular temperature has an energy that is given by kBT, where kB is a Boltzmann constant and T is a temperature, right? And what is the consequence of this energy? Yeah, I'm just going to say what is the consequence of energy in a couple of slides, but before that, I just come to this definition of these nanoparticles and colloids. Okay, colloids by nanoparticles by definition, it is any particle that has at least one dimension. Okay, at least one dimension in the size range from 1 nanometer to 100 nanometer. That's how a nanoparticle is defined, right? And similarly, what are called as colloids, they are a class of particles which include nanoparticle, that is 1 to 100 nanometer size range, plus something that is larger than that as well. Okay, so that means the size range of anything that is between 1 nanometer to 1 micrometer is what is called as a colloid. Okay, now this is just to give things in a perspective. Again, I picked this up from the from one of the sources. Let's see, if you look at football, right? Football is of the order of about centimeters, right? Typical size of the football would be not meters, right? It's centimeters, and typical size would be about 22 nanometers, right? So to say 22 centimeters, I'm sorry about that, right? And then if you there are different things that are listed here. For example, if you take human hair, that's about 80 micrometers. That's a typical size of a human hair. And then if you go and then think about these red blood cells, right, RBCs that are there in our body, right, that's typically about 7 micrometer, right? So therefore we are talking about something that's even smaller than that, right? Therefore these are okay. The reason why there's a lot of interest in particles that are of this size, okay, 1 nanometer to 1 micrometer, would become a bit clear if I talk about their widespread applications, okay, which I'm going to discuss in the next an hour or so. That brings me to the definition of what is called a colloidal dispersion. I've talked about only particles in certain size range, but the moment you put these particles in a liquid, okay, so what I've shown here is this red are the particles and this blue is a liquid, and in technical term these particles are what are called as a dispersed phase, and the medium in which they are put is what is called as a continuous phase, or a fluid medium in which the particles are embedded. And so therefore we can think about colloidal dispersions as a homogeneous solution, right, which contains some dispersed species, okay, and these dispersed species can be particles, right, that's what I've shown here. It could also be polymers, it could be some surfactant molecules, but anything that has a size range between 1 nanometer to 1 micrometer is what is called as a colloidal dispersion, okay. And one of the fascinating properties of the particles that are dispersed in fluid medium is, all of you may have heard of this name, Brownian motion, right? And Brownian motion basically occurs because the particles that you have in this medium, right, they respond to the thermal energy, and in this case, where does the thermal energy come from? It is from the environment, right? There are liquid molecules, and these liquid molecules have this energy kBT, and these are basically continuously bombarding with the particle that you have in the continuous medium, and because of that bombardment they move around, okay, and they move around in a very zigzag fashion. There is no particular direction, right, because it's all a probabilistic process, right, and they just go in a random, they basically take a random path, okay, and this is what is called as a Brownian motion, right. And this was something that Professor Robert Brown had kind of, had seen such a Brownian motion, but not with model particles, but with what are called as pollen grains, right? You may have heard of this story that, Robert Brown was trying to kind of understand the origin of life, okay? And he knew that, for example, I have an example, to discuss a little bit more further. So what he said is, these, bees go and sit on the pollen, right, on the flower, and then they kind of capture the pollen from one plant, and then they go, right? So that's how the pollination happened, right? And therefore, he was thinking that, the pollens have life, okay? And then when he put these, pollen in water, and they were kind of exhibiting this motion, and he thought that this motion that they're exhibiting is because of the fact that they have life, but actually that was not the case, right? They exhibited Brownian motion because of the bombardment of solvent molecules. That means their motion was not because of the fact that they had life, but that was because they were smaller in size, and the bombardment of particles is what led to these things, okay? So there's a nice history behind it, so maybe you can read up a bit more about, if you're interested more in that, right? And so this particular phenomena, as I said, Brownian motion was kind of studied by Robert Brown in 1827, right? Quite long ago. But actually, almost a century later, 1926, okay, which is almost, more than, just about 1 century later, there was a scientist by name John Perrin who got the Nobel Prize, okay, for studying this Brownian motion in a more quantitative way, okay. I also have a little bit of, a small story to tell about that, maybe a little later. Okay, that comes to a discussion on the source of particulate matter, okay. Any thoughts? Where do the particulate matter come from? Okay, we talked about these nanoparticles or colloids, size range between 1 nanometer to 1 micrometer, right? Have you thought about where do these particles come from? Because everybody talks about nanoparticles, nanoscience, nanotechnology, right? Okay, so therefore there should be some understanding as to where do these things come from, right? I mean, it can be a simple answer. I mean, you can just, maybe a few of you, if you can just speak out and let me know. What is that? Okay, so he says you take larger particles, you size, reducing the size, right? Okay, he says that you can take larger particles, and you can do that also. In fact, you do that mostly in the kitchen, right? For example, you take food grains and making atta out of it, right? That's basically reducing size, right? So he's talking about a case where I can get particles in this 1 nanometer to 1 micrometer size range by reducing size of larger stuff, right? That's one possible way. Yeah, thank you for that answer. Anything else? Yeah. So he says a combination of atoms and molecules, if you put them together, it becomes a larger stuff. Yeah, go ahead.
So it could be that there's a particular compound or material for which it's more energetically stable to stay in that small size instead of becoming bigger. So naturally itself, when you prepare it, it conforms in that state. Okay, so he talks about a case where naturally itself, okay, so he is saying that there are certain things, okay, they are naturally available, and in their state, maybe the energy is minimized and they continue to exist in that smaller length scale. Okay, these are all very nice answers. Anything more? Anyone? Huh?
Bacteria, like they're in that cells, right?
Yeah, bacteria. So if somebody say, the bacteria are in the size. These are all very nice answers, by the way. Okay, and as you will see, I'm going to pick some of those things and then explain a little bit more about these nanoparticles. Okay, so the couple of answers that came about. Okay, number one was reducing the size from larger to smaller, and other answer that came from putting things together and then making it bigger, right? They kind of form the two class of methods. Okay, they form the two class of methods which are very commonly used for making nanomaterials. Okay, one is what is called as a top-down approach, that is reducing the size from a larger one to a smaller one, the top-down way of making particles, right? Other one that he mentioned is a bottom-up, right? You start with smaller stuff, put them together, and then make it bigger, right? Okay, so therefore these are two nice class of methods that everybody uses for making nanomaterials. And other things that are mentioned about the natural occurrence of either a particular compound or a bacteria is again another source of nanoparticles, and I'll discuss a little bit more about that in the upcoming slides, right? Yeah, just to add a bit more stuff to what you guys have said, we know that the industrial processes can also lead to nanoparticles, right? Because if you go to an industry, there are a lot of, for example, cement manufacturing, right? It has raw materials come in, right? And things are going from one stage to the other stage. There are a lot of these big crushing or grinding machines, right? When they do that, so a lot of industrial processes can lead to, colloidal scale particle generation. Vehicular emissions, okay? I know when people talk about emissions from vehicles, right? People talk about NOx and SOx emissions, right? Along with that, people talk about particulate matter as well, right? Because because of the incomplete combustion, right? What will happen is some of the stuff that comes out of the vehicular emissions does contain some particles. And other nice examples that all of you are kind of maybe aware of or used to at home is burning of candle and camphor. Okay, I just have an example of that. So it turns out that whenever you burn anything, right, at home, especially candle and camphor, you'll see that it leads to, you may have seen some nice flakes floating around, right? These are actually particles. Okay, so but it turns out that if you look at all these processes, right, industrial processes, vehicular emission, burning, they produce particles that have a complex shape and structure. Okay, the reason why, okay, they produce these complex structures is because all these processes are kind of done under a little bit uncontrolled conditions, right? Because when you're burning candle, somebody could be doing at some place the temperature could be 25, at some place the temperature could be 35, for example. Okay, and in some cases somebody may be burning candle from source 1 versus source 2. Okay, availability of air, right? There could be a room with more air, less air, right? So whenever all these processes are occurring, but under conditions which are slightly different from place to place, right? Therefore, when particles are generated out of these things, they typically have a complex shape and complex structure, and therefore that's because their formation is not occurring in not a controlled environment, right? And the reason why there's an interest in looking at particulate matter from these sources, right? All these industrial sources, is because for example, there'll be people who are trying to kind of assess health hazard, for example, freight and transport of aerosols, and I'm going to give an example of what is called as you can exploit these uncontrolled formation of particles for designing a super hydrophobic surface. I'm going to tell a little bit about that. So I just want to point that, so there are people who are trying to understand the particulate formation from these uncontrolled processes because they have implications in the health of people working in the industry, for example. They have implications in terms of, because once these are produced, what will happen is they are kind of transported, right? So these aerosols, okay, by definition are the particulate matter dispersed in air, right? And when there's a vehicular emission, the particulate matter are kind of carried from one place to other place. People inhale it, right? They can go into your lungs, for example. There's going to be deposition of particles, right? So therefore, people are trying to, there are a class of people, mostly from the environmental kind of section, who are trying to understand the formation of these things, the transport of these things, how do we control these things, how do we design filters for eliminating these things. Okay, these are some of the areas that people work on, right? Okay, any questions so far? Any questions so far? So I'm just going to give an example of a study that appeared in one of the prestigious journals. That's in a journal called Science, okay, which is one of the really big journals in publishing literature. And this one of the nice things about this paper is very simple. Anybody could have done this, okay? Anybody, even all of you could have done this, okay? All they do is a very simple thing. they take a candle, right? And when you burn the candle, as I said, the soot forms, and then they have a glass slide, and then they deposit, because the soot, right, it deposits on the glass slide. And what they do is they look at the structure of the soot that is formed. You see, I mean, it's kind of flaky in structure, right? It has a, kind of it has, so this scale bar is about 100 nanometers. This scale bar is 100 nanometers. Therefore, each particle would be maybe about, I don't know, 40, 50 nanometers in size, right? And they kind of look like a loosely bound aggregates, right? These are aggregate particles because there are many particles, put together, right? And when you see, this, when you burn candle or camphor, when you see this soot floating, right? You should basically imagine something like this, right? Okay, it is basically a collection of small nanoparticles, aggregated together or joined together by some forces. In this case, is van der Waals force. Okay, and what they do is this. Okay, very simple experiment. You deposit them on the glass slide. Look at the structure, and then so it turns out that when you deposit like this, okay. After the deposition, I take this glass slide with the soot form. Then if I put a small drop of water, okay, if I put in a drop of water, the drop of water takes a shape like this. Okay, that's your glass slide. Okay, that's a small layer of soot. Okay, and if you put in a drop, okay, I'm sorry about my drawing, so that's going to be okay, you should imagine a spherical drop, right? So it takes a shape like this, right? So that means when I have a glass with soot, if you put a drop of water, it doesn't spread continuously, right? It doesn't spread. It takes a shape of a perfect sphere. Okay, and I think I have a few slides later. I'm going to explain a little bit of that. So this is what is called as an example of a super hydrophobic surface. Okay, that means I have a surface coated with soot, and water doesn't like to spread nicely. It takes the shape of a perfect sphere, and that's because this water wants to minimize its contact with water, the surface, and such surfaces are what are called as super hydrophobic surfaces. Okay, right? There's what is called a super hydrophilicity, where things completely wet, super hydrophobic when things don't wet at all. Okay, and there's an interest in making such structures or such materials because, for example, yeah, you have some question? No. Okay, so because there are people who are trying to make what are called as anti-icing surfaces, for example, right? When for example, soot is not a best example, but if I can make a transparent, coating which gives super hydrophobicity, it's great because, for example, say that there's somebody who's flying an airplane, right? You don't want the windshields and the these glasses to be covered with ice, right? Because you don't want the deposition of liquid. If it deposits, it freezes and it kind of reduces visibility, right? So, but if you have surfaces which are super hydrophobic surfaces, then the deposition doesn't occur. The moment it comes in contact with these surfaces, it just rolls off, right? And so therefore, there are people trying to look at some of these aspects. So yeah, go ahead.
What is the difference between hydrophobic and super hydrophobic?
Oh, that's a good point. Okay, so yeah, so when I have a surface, right? If I put in a drop, liquid drop, right? When it completely spreads, people talk about, okay, let me just draw something first. Okay. So this is your solid surface, right? This is your, say, gas or air. This is water or liquid, right? Okay. At this particular point, right, is what is called as a three-phase contact point, because that's where the gas, water and the solid meet. And what people do is they draw a tangent at the three-phase point and they define a property called contact angle. Okay, so all this definition of hydrophobic, okay, or super hydrophobic, hydrophilic, okay, or super hydrophilic, okay. It all depends on this angle theta, okay. So super hydrophilic, the theta should be typically of the order of 0 degrees. Super hydrophobic, typically is supposed to be something greater than about 140 to about 180, okay. I don't know the lower limit, but closer to 180 is what is super hydrophobic, right? And anything that is in between, for example, people say 0 to 90 can be taken it as hydrophilic, okay, okay, and 90 to 180 is supposed to be hydrophobic, okay. But super hydrophobic is something where the contact angle is greater to 180, and super hydrophilic when the contact angle is closer to 0. Yeah. Okay. Any more questions? So, yeah, maybe I'll take you first. Yeah, go ahead.
Yeah, so these nanoparticles, they are also present in materials of larger scope.
Yeah.
So why is it that they show these properties only when they are in this small form factor instead of as a whole material?
So if you look at any classical textbooks on nanoparticle stuff, right? People talk about two important properties. One is surface area, right? Surface area is typically defined as, if I have a spherical particle, right, 4 pi r square is the surface area, and we know that if I take a larger material, for example one like this, okay, and I break the same into many more smaller particles, right, then the surface area in this case is going to be much larger, right? And the reason why this is important is because for example, say there is a water, okay, with some for example, like say industrial wastewater, okay. If this industrial wastewater has dye, okay, right, and if I want to remove it, right, what people typically do is they go to these nanomaterials which have higher surface area, and if I choose my nanomaterial appropriately such that this dye kind of absorbs onto these things, because of the fact that I have a larger surface area for a smaller materials, that's why there's a lot of interest in looking at such materials, okay. So basically functional properties of materials can be enhanced by using nanomaterials. Could be one possible answer. Yeah.
Sir, so when there's a super hydrophilic surface,
Correct.
does it also make evaporation tougher off of the surface? If this surface is super hydrophilic, I put some water there, will it be tougher for it to evaporate compared to?
Okay. That's a good point. So what he's trying to say is that I have two cases. Maybe okay. This is, let us say this is a hydrophilic surface, and this is a hydrophobic surface. So he's talking about he's talking about a case where I have put water on this and water on this. Will the water evaporation be harder in this case, tougher, right? That's what you're saying.
Lowers the potential energy of the water.
So, but yeah, before we even think about that question, but if you look at the surface area, right? See, evaporation is a surface phenomena, right? Right? So therefore, if I look at a case where I have a same volume of drop and it spreads nicely, the total surface area is larger, right? Compared to a case where it's like this, right? Therefore, because of the fact that on a hydrophilic surface, the area is larger, therefore the evaporation is supposed to be much larger here compared to this, right? Okay. Now, I would say that's the first thing that we should think about, okay? And of course, then the next question is, if I have two cases, right? Both of them are hydrophilic, okay? One has, for example, I could have a surface which is atomically smooth, okay? Or I could have a case where I have a surface which still gives a contact angle of 0, the liquid nicely spread, but it may have some some nanoscale roughness or something like that, right? So yeah, evaporation in these two cases, because of the area is the same, the fact that one is atomically smooth and they have these perforations, that could kind of change the evaporation pattern, but that depends again on the binding of water molecules, surfaces and stuff like that. Okay, yeah. Okay, any other questions? Yeah.
So in the case where there's a droplet of water over this layer of soot, it's in a stable equilibrium.
I would say that these are all. So when you say stable equilibrium, so one of the way to think about this would be that. So see, I can think about when you talk about stable equilibrium, I can say that you can think about. See, typically whenever we say something is stable, right? One of the things that everybody thinks about is energy minimization. Right? In this case, for the given substrate and the given fluid, right? That's the energy minimum state. Okay, so that's maybe that's how you can think about it at this point. Yeah. Okay. Therefore, given the combination of the substrate and the fluid, okay, and the drop taking this shape is the stable configuration. Yeah.
Like for example, if you were to deform the droplet a little bit, like not supplying enough energy for it to break apart, but deforming it a little bit, will it come back to its original state and then go back?
Yeah, that's a good point. So because see, all these processes that you're talking about, right? So what he's saying is, what if I put in a drop, okay? I slightly deform it a little bit, okay? All these things would happen. For example, how do you create a configuration like this? What you do is you take a substrate. I have a syringe, right? I make a drop, and then there are a lot of people who are studying the dynamics of drops itself. Okay, what happens to a drop when it impacts the substrate? Okay, what are the initial shape fluctuation that it undergoes? Okay, and what is its approach to equilibrium? Okay, what happens to the drop shape once it attains equilibrium? Okay, all these are very important processes, right? In fact, there are one of the things that people learn when this interfaces are introduced. Okay, is that if I take a water drop in the form of a cube, okay, let us say I have a way of creating water drop in the form of a cube, and I take this cube and put it on any surface, right? Or imagine I'm able to kind of have a cube of water suspended in air, for example. Okay, a hypothetical experiment. Then if you look for energy minimization, right, the surface tension will ensure that it ultimately will take a shape of a perfect sphere, right? And that occurs because this is a minimum energy state compared to this, right? So therefore these shape fluctuations can happen, okay, but equilibrium shape is actually governed by the interfacial forces involved and things like that. Yep. Okay. Any questions? Okay, so I talked about a case where these particles are made in an uncontrolled way, right? Vehicular emissions, or what is it? Burning of candles and stuff like that, right? Or industrial processes, right? Now, these are examples of cases where particles have been made in the lab. Okay, these are all examples from our own lab, right? Where we were able to make this very nice spherical looking particles. So this is a scale bar, is about 500 nanometers, and these are some rice-like particles, right? They look like rice, but only thing is much smaller in size. The scale bar is again about 500 nanometers. Therefore, the length of these would be about 200 plus nanometers. And these are kind of polystyrene beads, again made in a particular way. And so therefore, if you look at these things, they appear much more nicer, right? So therefore, if you look at a lot of work that is happening in the nanoparticle literature, It is done by taking particles of well-defined size and shape. Okay. The reason why that is important is because whenever you want to understand any fundamental principles, okay, whenever you want to understand any fundamental principles, knowing what particles are, what is their size, what is their shape, what is their charge, okay, all the fundamental properties of particles are very, very important. Therefore, people have come up with very nice synthesis procedures, okay, and people in this building, chemists, right, chemistry people, what they do is they have a lab in which they all their life they talk about, some people are interested to make particles, okay, they come up with easily, easy procedures. For example, okay, one pot synthesis, you put everything together, magic, particles appear, right? Okay, there are people who kind of devote a lot of life, making these things, and one such procedure is what is called a Stober method. Okay, Stober was a scientist from Netherlands, from one of the very famous labs in Utrecht. Okay, Utrecht is I don't know how many of you have heard Utrecht University. Okay, Utrecht University is at Netherlands, right? And people like Van der Waals, right? You have heard of Van der Waals forces, right? And Debye, right? So all these people came from this lab. Okay, it's like mecca of colloids. Anybody who wants to work with colloids should go there, right? So there are people who have come up with very nice procedures, and although we do this in our lab, I'm not a chemist, right? I'm a chemical engineer, but the procedures are so nicely laid out that you don't have to know everything. Okay, the recipe is given. It's like cooking rice, right? You need water, a little bit of salt, maybe, right? Rice, right amount, everything, and rice gets cooked, right? Exactly like that. Okay, but only thing is, of course, one has to worry about lab safety, handling chemicals. You have to do things in a particular way, controlling temperature, all of that. But if you do all of this, then making these colloids is very, very easy. Okay. So therefore, two things, right? One is, okay, you can get particles from the industrial processes and burning camphor and stuff like that. Second thing is you can synthesize them in the lab, and these particles that you see here, they are done by a very simple, okay, yeah, maybe I can come back to that a little later. So what people have done is they have kind of come up with some kind of like say rules, if I want to call it as. So this is dP is a diameter of the particle that I can produce here, and the chemicals involved in making these particles, right, is you need water, H2O, you need ammonia, NH3, that acts as a catalyst, right, and you need this TEOS, it's called tetraethyl orthosilicate, not important at this point, but it's a source of silica, Si molecules are there, right, and you can see, right, if I want a particle of particular size, okay, I should know what is A, right, and that depends on the concentrations, and I should know what is B, that depends on the concentration of ammonia, right, and therefore I can actually tune the concentrations and I can actually achieve particle of particular size, right. People have come up with very nice procedures like this, okay, therefore you don't have to really break your head, right, everything has been done, right. So now this is one of the simplest ways of making particles, okay, and we did that in the lab, a couple of years ago. And we kind of published a paper in which what we said is this, okay, if you look at plastics, right, if you look at plastic, this is important because everybody talks about sustainability these days, right, okay, people are using too much of plastic, what do you do with it, right. So we can, of course, the nanoprecipitation is a method which is known in the literature, okay, and the process is very simple, right. You take a polymer, okay, and polymer should be in what is called a good solvent. When I say good solvent, all it means is that if you take this polymer, put in this solvent, it becomes a molecular solution, okay. That means all these, this green stuff that you see, these are polymer molecules in a liquid, okay. And some of the good solvents, if you take polystyrene, right, when you buy any electronic gadget, okay, that white stuff that you have, styrofoam, right, The styrofoam is actually a polystyrene with about 98% air or 90%, 8% empty stuff and only 2% polymer. One of the problem with that is it occupies large space, okay? People do landfilling, right? But for landfilling, because it's very bulky, you need large area, okay? And once you buy it, people are using it for, for example, cups made of polystyrene, plates made of polystyrene. People use it in some rituals, for example, right? And stuff like that, which is not great, right? Because it accumulates everywhere, right? You have seen in streets where people have kind of thrown these things around. So what we did is we took polystyrene, the same thing, and it dissolves nicely in a lot of solvents. Okay, THF is one. Okay, it's called tetrahydrofuran acetone, very commonly available. For example, nail polish, right? It has some nail polish do have acetone. You need some of these solvents. So therefore, you get a molecular solution of this polymer, and all you have to do is take another fluid, okay? And this fluid should be a non-solvent for polystyrene. What do I mean by that? The moment you put this in this polymer does not like to be in this solvent, and what it will do? It will come out. Okay, it will what I call it, precipitate. Okay, and when it precipitates in the form of particles. Very simple process. You can do this in 5 minutes. Okay, all you need is, if somebody tells you, do you know how to make nanoparticles? One recipe could be this: nanoprecipitation. Take a polymer and a solvent, mix them up, take a beaker containing water, just add it up. That's it, nothing more than that, right? The only issue is that, the particles that you get are not nice, right? They're polydispersed, right? They're of all different sizes. There are people who are trying to understand the packing of such particles and stuff like that. It could be a nice model system for them. But currently what we're trying to do is to kind of come up with ways by which I can make particles that look identical. Okay, we are kind of looking at some new technologies in the lab where I can take a waste polymer like this and then make particles of exactly identical size. And if I want to do that, I'm going to make a lot of money, because we buy particles in the lab. Okay, we buy particles from commercial sources. Okay, it comes as a bottle, okay, with about 8 ml of fluid. Okay, 8 or 4 depends on what you order, and it contains 8% solids. Okay, and only thing is they are nice and spherical and monodispersed. They look identical, and for this we pay about 30,000 rupees per bottle. Okay, now if I can take waste, if I can make nice particle like this, okay, which we're kind of trying to work on at this point, you can do a startup and stuff like that, and that will, okay, money is one, but you're trying to also think about, taking a waste material and then see if I can convert it into something useful, right? And it turns out these particles, right, they're used in a lot of applications. People are using as, biomarkers. For example, you can inject a fluid which contain these particles and then trying to look at, maybe a location where there could be some issues in the cells, for example, and stuff like that. Okay, so there are a lot of implications of these materials, and if you can achieve, making these monodispersed particles, it will be a nice, thing to do. Yeah, may not be important. Okay, coming back to natural origin, right? Somebody mentioned that that there are things that are available naturally. And this is a plant that you see everywhere in the campus. I don't know if you notice, right? If you walk around, right? We have a very nice paper that came up recently, in which we used a fluid that comes from this plant. Okay, it also had a newspaper coverage and stuff like that. Okay, so what we do is we take this plant, right? If you basically cut a small portion of the leaf, right? A white fluid comes out, right? And that sap actually has these particles. Okay, this is a scale bar. It's about 2 micrometer going from here to here, and as you can see, it has nanoparticles, and they have some interesting properties. People from pharmacy background are trying to look at these fluids, for example, in some applications and stuff like that. But we looked at the colloidal characteristics of these plants, and we've done some nice work. Maybe I can talk a little bit about that. And the other example is because of the COVID pandemic, right? Everybody knows viruses, right? COVID virus is one. For example, this is an example of a virus that is called FD virus, and that's a long rod-like virus. The size of this is about 880 nanometers in the length, and it's about in the diameter it's about 6.8 to 7 nanometers. And if you look at E. coli, right? E. coli is a bacteria, right? And as you can see, this is again about a couple of microns in sizes. So therefore, there are people who are trying to use these biological the occurring entities, for example viruses and bacteria, and because of the fact that they kind of have a size range, okay, right? This again falls into the nice colloidal size range, right? 1 nanometer to 1 micrometer, and they use them as model colloids to study some interesting phenomena, okay? And those interesting phenomena I'm going to talk a little bit about a little later. Okay, and this is a example that I was talking about. This top-down approach is where you start with a larger stuff and make a smaller one. And this is a video, hopefully it's going to play. And all of you know this, right? I can take a larger stuff. If I basically, crush it, all that happens, everything breaks up into smaller sizes, right? Only thing is what people do is they kind of have come up with some nice devices for doing it. One such device is what is called a ball mill. Okay, it's a nice simple device. You may also have seen this, in construction sites, no? People use it for mixing as well. Okay, it's a simple device which has basically a cylindrical drum, and in the cylindrical drum there are these large, spherical balls. Typically, they are made up of high strength materials, for example, steel or some ceramic or something like that. And then in between them there are the smaller ones. That's your feed, right? And the feed is basically charged into a drum along with this the high strength material, and when you rotate it, what will happen is these beads are, right, they are carried to the top and they fall down, right? And when they fall down, there's an impact, right? Whatever material that you have at the bottom here, that basically gets crushed up, right? So therefore, this high energy ball milling, okay, is a very simple technique that everybody uses in the lab, especially people from metallurgy background, right? They use this high energy ball milling for reducing the size from larger to smaller. And if the size range comes out to be 1 nanometer to 1 micrometer, then you are able to produce colloidal scale particles by this technique. Yeah, maybe I'll just stop here. If you have any questions, I'll be happy to take them now. Maybe after the break, I'll just spend a little bit of time talking about motivation to study colloids. Okay, I've given some examples already, but I just want to end my part of introducing you guys to nanoparticles and colloids by taking examples from different fields, right? And then tell you a little bit about what is so fascinating about these nanoparticles and colloids, and what is the reason for studying them, and we'll talk about different people who have kind of contributed to this particular field in after the break. Yeah. Any questions? Yeah. Yeah. Bottom-up approach, as I said, one simple way is the synthesis, right? Okay. Typically, as I said, right? Okay. So this is top-down, right? We said ball milling, right? Bottom-up is basically reverse, right? And as somebody rightly said, here what you're doing is you're bringing the atoms and the molecules together to make a larger stuff, right? And one of the simplest way of doing this would be by chemical synthesis, right? For example, one of the well-known chemical synthesis route that I know is making gold nanoparticles, right? AU, right? And you will see gold nanoparticles being used in a lot of different applications. So there, the reaction is something like, what they do is they start with a gold salt, okay? Something like AuHCl4, okay? Gold orochloric acid. And what they do is, so if you want to make gold nanoparticle, I'm supposed to do what is called a reduction reaction. They typically use a reducing agent, something called as a ascorbic acid, okay, or citric acid, and that basically leads to the formation of AU nuclei to begin with, okay, and many more atoms join together to basically make a bigger. Okay, so this is one example, and the example that I gave on this nanoprecipitation, right, is again a bottom-up approach, right? Because you're starting with molecules of polystyrene or any polymer in this solution, and then you're doing precipitation, and many molecules come together and they form these larger stuff, right? That's also an example of a bottom-up approach for making particles. Yeah.
So when you're using reactions to like synthesize compounds, you get them in a bulk, right? So again, you'd have to break them down to like small.
Tell me again.
Like, this is what I think.
You go ahead.
So when you're synthesizing something, you use like reactions, right?
Yeah.
And you get them in like a bulk. So that also you have to break.
Sure. So what is saying is, so when I buy a chemical, right? Maybe in the chemistry labs, if you've seen, it comes as a bottle, right? And in the bottle there could be chunks of the raw materials, right? That's what you're trying to say, right? Yeah. So as I said, if you want to make these silica particles, right? I need to have this ammonia, water, and TOS, right? These are the reagents, right? Now, typically this is a simple reaction which is typically carried out at room temperature, for example. What you do is you mix all these things under certain conditions, right? When we say 25 degrees centigrade, you put in a constant temperature bath and wait for some time, okay? And as soon as that is done, okay, and if you wait for the reaction to complete, what you will get is a dispersion of these particles in the reaction media, right? For example, it will have, some unreacted ammonia, maybe, definitely water, right? And maybe, depending upon the extent of reaction, TOS would have completely consumed, right? TOS may not be there, right? There is this concept of excess reactants and stuff like that, right? So therefore, in the end, the reaction mixture would have, maybe unused up reactants plus some maybe water or other fluids along with these particles, right? And if you're done, of course, there are cases where these particles can fuse and become a bigger mass. But if you have carried out reactions under controlled conditions, there are some stabilization mechanisms people talk about, right? When you produce these particles, it turns out that these particles have certain surface charges, okay? These surface charges kind of prevents them from coming to close distances. If this stabilization mechanism was not there, then particles would stick, they become aggregates, they become, then there's an uncontrolled reaction, for example, then they become much larger in size, right? Those are difficult to kind of separate out, okay? But what people do is, when they're trying to do these reactions, they put in some stabilizing agents together with these things, and that will ensure that these particles remain as individual units. Therefore, what you are getting actually is a nice dispersion of these individual particles in the fluid, and separating them is typically by centrifugation and stuff like that. So you can basically sediment them if they are heavy enough, or you can use centrifugal sedimentation kind of processes, and then you can sediment them and take them out.
So force of attraction between the particle and the fluid should be greater than the force of attraction between the particle and the particle.
The better way to, you can bring in the concept of force between the particles and force between the particle and the fluid as well, right? But for this particular processes, maybe the interaction between the particles would be the best way to do it, okay? So if you look at interaction between these particles, one of the interactions is van der Waals forces, right? And there could be, for stabilization, you need something where there's a repulsion, right? If the van der Waals take over, there's going to be aggregation, but you don't want that to happen. Therefore, people come up with some mechanisms by which I can induce repulsive forces between the particles. Okay, so maybe there's a break now, no? About 5 minutes of break, right? So maybe we'll just break for about 5 minutes or so, and then we can, resume the session.